Okay, in case folks didn't hear, I think question 2 on the quiz today is asking you, what is the minimum number of steps that the snake has to take to get from this bottom left corner to the super amazing Oreo? You cannot go down, so it does not roll around. So the question was, could the snake go down and he would pop up here? The answer is no. Imagine that this grid is surrounded by X's. So there's a lot. That's a great question. Thank you for clarifying that. Okay, so it's 12 o'clock. We're already recording. I'm going to turn off my videos, guys, on Zoom. But if you have any questions on the quiz, please feel free to speak up. Or actually, maybe I'll leave my video on this time. Oh, actually, quick question. Does anybody have a charger for a MacBook? Like a USB-C charger that I can borrow for the remaining of the class? No? We might be able to make it, but I'm at 36%. I mean, I left one. Okay, somebody's got this one. Let's see where I can plug you in. Thanks, Vincent. Okay, it's a phone charger, but hopefully that keeps us alive. So if anybody else happens to have a USB-C charger that you'll let me borrow. Oh, you do? You have a big one. Oh, thank you. And I will 100% give it back to you after class. Just remind me as well. Thank you, thank you. Great. Thank you. Thank you. Appreciate it. All right, guys, quiz time. Do you guys have any questions? In case anybody showed up late for the question 2, there's imagine there are X's all around the border. Okay. So the snake, if he moves down, he cannot pop up back at the top. It's like there's a wall surrounding everything. Okay. Great. How's it going? Took it on your phone? Great. That's great. How do you normally do notes? Do you have a notebook or you just listen to the lecture? You just listen. All right. That's good. Let's go back here, guys. Any questions on the? Yeah.
So, I don't know about this topological sorting. Where do we start? So we can start anywhere.
So topological sorting is where you sort the nodes such that the nodes that come before have no dependencies on nodes after.
Okay.
Right. So it's when we did the dependency graph, we were like, what do we install first? Right. Yeah. So, but you can, for this one, there are 2 places you can start. So C and F there are many valid ways to sort this topologically, but only one of these is valid. Yeah. Right. So we had a pretty good question in the back. Just bringing it to you guys. If you are working on this question that is asking about valid topological sorting. If you guys remember, a topological sort is where we did the sorting with the dependencies, the D package, like what do we install first, right? So a valid topological sorting is one where the node that comes, when you get to a node, you have already installed anything that could point to it, right? So there are many valid sortings, but only one of these is valid. For example, the very first one says to install A first. That's clearly not a valid topological sorting because it depends on D, it depends on E, it depends on D. Because maybe one thing to notice is that A kind of depends on a lot of stuff, so it should really be last. Welcome to class. We're just doing our quiz like every Monday. Any questions from the folks on Zoom? Michaela, Joel, Jarvis, anyone? No? Okay. Oh. Yeah, all right. Yep. Question? Oh, yeah. So from the course website, yeah. I just put them here just to remind you guys on Blackboard. But the course, yeah, yeah. Well, again, just a reminder, folks, if you want to access the quiz, there's two main ways. If you go to the course website, the announcements has the link to the quiz, and then also the lecture for today. Lecture 19. This also has the link to the quiz. And if you have the slides open already, that also has the link to the quiz. Hey, welcome to class. We're doing quiz 6. Well, I think, how are you guys feeling about the quiz? Confused in a certain question? All right, let's talk about it. Which one? This one? Yeah. Not necessarily. Yeah, so that is a good question. So intuitively, if we were doing, if we did DFS to come up with a topological sorting, it is true that the topological sorting DFS comes up with will have the connected components in sequence. But the definition of topological sorting is just a sorting where by the time you get to a node, all the nodes that it depends on are already in the, like, came before it. Okay, so yeah, we can talk about this one, for example. So I think this one's the right answer, FDCAEB. So you're right that it starts with F, which is fine. Then it goes to D, which is okay because the only thing D depends on is F, and F already came before in the sorting, right? And then it jumps to C, which is also okay because C doesn't depend on anything. So actually C could go anywhere. So there is like another sorting where you start with C and then go to FD, right? So in general, topological sorting, the only thing it means is if a node came before you in the ordering, by the time you come in the ordering, everything you depend on should have come before you. Okay, yeah, but that is a great question. And you are right that if we ran DFS to find a sorting, so there are many valid sortings, but if we ran DFS to find a sorting, they would be connected because the way DFS works, it reaches all the connected pieces. So it would probably do like, it would do like F, D, E, C, B, A, or something like that. Yeah. All right. That's a great question. Any other questions on the quiz before we get started on lecture today? Okay. All right. So let's go ahead and get started on lecture. Again, the quiz is open until midnight. Please get it submitted. This quiz is a little bit interesting because it has a lot more open questions. But yeah, just get it submitted when you get a chance. All righty. All right. Cool. So today we're going to cover some really cool stuff in addition to quiz 6. Again, reminder, the in-class midterm is this Friday, March 4th. Okay, this Friday is not a mental health day, as far as I'm aware, for the school. It is not a mental health day for our class. There may be some classes you're in where it is a mental health day, but we are having class on Friday and we are having the midterm on Friday. Now, after that, you have spring break, and the following Monday, our class does not meet. We have a mental health day on that day for our class. I don't know about your other classes, all right? So you do have an extended spring break, maybe, depending on what your other classes do, right? Does that make sense to everyone? So you should come here Friday to take the midterm, okay? If you don't come and you tell me, oh, I thought there weren't classes, that's not really a valid excuse, I would say. So, yeah. Cool. Other things about the midterm. So yeah, you guys, again, reminders, like check out the course website. We do have some practice questions, practice solutions. And I've opened up all the quizzes. So the quizzes are now reopened. You can click through the quizzes. You can review the answers. You can actually see what the correct answers are. So I've opened them all up. Same for the homework 0 to homework 5. I think we are going to release homework 5 solutions pretty soon because they were due on Friday. But all the other homework assignments, we have released all the solutions as well. So you're more than welcome to look at those. And then obviously lecture 0 to lecture 18, those are just the lectures. All of that material is fair game. The stuff we're going to cover today is not on your midterm. Right? So today you don't even have to pay attention. I'm kidding. Hopefully you do pay attention. And we are having a review session on Wednesday. So come prepared with questions. If there's something on the practice midterm that you couldn't figure out or don't understand, right? That would be great. The other thing is I am giving a few bonus points on the midterm itself for everyone that has completed, that has submitted all their assignments and all their homework up to when we take the midterm. So if you've done that already, you're awesome. If you haven't, you have a little bit of time to submit corrections up to the midterm, and then you can get a few bonus points. If you don't submit up to the midterm, you can still submit corrections after, you just won't get bonus points on the midterm, okay? Cool. So it might be a good opportunity to like as you're studying, you can like correct your homework, for example, and then email it to me. Any questions on that? Cool. I really want to make the midterm difficult, so please study a lot, you have no homework this week. So the time you would have used to do the homework, please use it to study. Awesome. All right, so again, today, not on the midterm, but we are going to review Kosterajou's algorithm for finding strongly connected components on a directed graph. And then we are going to introduce weighted graphs, and we're going to talk about a few examples where weighted graphs are useful. And we're going to motivate Dijkstra's algorithm, which is a shortest path, single source shortest path algorithm on weighted graphs. So we already have a single source shortest path algorithm called BFS for unweighted graphs, right? Breadth first search gives us the shortest path from any one node to any other node, okay? All right, so this is what our goals are for today. Let's do a quick recap like we said at first. So the algorithm we covered on Friday, we talked about finding connected components in linear time of n plus m. Who wants to remind me what the algorithm does? You guys remember what the steps were for the algorithm? Okay, I'm hearing a couple of answers. Yes, so the first thing you do is you run depth first search on your graph to create a depth first search forest. You can choose your starting vertex in any order, right? Because you don't know which one to pick first. And you keep track of the finishing times, okay? Then you go to your original graph and you reverse all the edges, right? So if I had an edge from A to B, you reverse it. So then now it's an edge from B to A, okay? Then you run DFS again to create another depth first search forest, okay? But this time you tackle the nodes in reverse order of finishing times. So DFS, you call it on the node that has the highest finish time. And if you ever need to call it again, you know, you're restarting to start a new tree, you call it on the next node that has the highest finishing time from your original DFS, okay? And then the claim is that the strongly connected components are each of the trees in our second DFS forest, okay? Who wants to remind me what is a strongly connected component? Yeah. Loop, close. No, it doesn't have to do with loop. So yeah, Vincent. Right. So a strongly connected component, I think you guys were basically both right, is a set of nodes in our graph where for every pair within that set of nodes, you can go from node U to node V, and you can go back from V to U, right? So it creates a cycle, like you said, and means that you go to it and you can go back from it, right? That's a strongly connected component. Why do we care about strongly connected components? You guys remember why it might be useful to find the strongly connected components in a graph? What might it tell us about relationships or groups of people? Yeah.
You said you mentioned that it can be used for like communities.
Yeah. Yeah, and we're going to see some examples of that sort of stuff. But yeah, basically, if you have a very large graph, it can really help you identify communities within that graph. You can intuitively, you would think that a community is a strongly connected component. That is one way to define a community if you don't know any other information, right? Cool. Last time we ended with this algorithm, but we didn't really understand why it works. All right, so today we're going to talk about why it works. So again, here's the example we covered from last time. So again, the very first thing we do in the algorithm is what? If I have a graph, what's the very first thing I do? I run depth first search and I keep track of the finish times, okay? So start with any vertex and you run depth first search. So here I actually started with this one because the start time is 0. And last time we walked through each step, but at the end of the day, we run depth first search to discover on the entire graph, right? And we keep track of the finish time. The finish time is when I finish a node, right? When I exit. What do we do next? Yeah. You reverse the direction of the edges. Okay. So that's from here to here. We reverse the edges. All the edges have been reversed. And then what do we do after that? Depth first search again. Where do I start? Highest finish time. So I start with this one. I run depth first search. It can't go anywhere. Kind of nice that happened, that it can't go anywhere, because this is a single connected component on its own. Okay. So I finish. That gives me one tree in my depth first search forest. So I say, this is my strongly connected component, right? What node do I go to next? Where do I run my depth first search after this? Next highest, which is which one? The ANT, yes. So I started ANT, I run depth first search. I have two options. I could go here, I could go here. It doesn't matter which one I go to, right? So it's only when I'm picking the starting node that I care about the finish time. But let's say I go here. And then from here, I really only have one option, right? Because this edge is going in, so I can't go here. I go back to Wikipedia. And then from here, I have nowhere to go. This one I've already visited. This one I can't go back. And this one is an edge coming in, so I can't go out of it, right? And luckily enough, this also is a strongly connected component of my graph. So with my second DFS tree, I have now identified the second strongly connected component. What node do I do my DFS on next? The dog. Yeah. Start with the little cute dog. I run DFS. I go to Google. I'm done. And luckily enough, this is my third strongly connected component. Okay. So again, that's the algorithm. That's how it works. So you guys should hopefully understand. Now we're going to talk about why it works. Okay. So this is the graph that we call the strongly connected component graph, okay? Because we have identified strongly connected components. And as a thought experiment, what we're going to do is we're going to pretend that each strongly connected component is a vertex in a new graph. This is called like a meta graph. Again, we don't do this in the actual algorithm, but in order to understand why it works, we're going to pretend, we're going to think about it. This is a thought experiment. This is like Einstein's experiment about like how fast light travels, right? He doesn't actually do the experiment, he just thinks about it, right? So if we pretend that each of these is a node, so again, you forgot there was stuff in here, you just pretend this is an entire node, right? Then we notice that this graph here is a directed acyclic graph. Why is that the case? Why is the graph made up of strongly connected components where each strongly connected component is a node? Why does that become a directed acyclic graph? So it's directed because our graph was directed to start with. So that should be obvious. It's a graph because our graph was a graph to start with. So the question really is, why is it acyclic? Why can there not be cycles in this graph? Or yeah, so there's nothing going in. So for this example, it is definitely acyclic. But why can it never be? Why can we say that in general, the graph that is made up of, let me take my strongly connected components, okay, and make them into a node? Why can the resulting graph not have any cycles? Yeah. If there was a cycle, then I would be able to merge these two connected components, right? Because this connected component is saying, okay, I can get from any node in here to any other node, right? This one is saying, I can from any node in here to any other node. So if I had a cycle, if I had an edge here, edge going here, maybe edge going here, then that means that I can get from any node here to any node here, right? I can just follow the cycle. This, like, if I want to go from here to here, I just take this edge. If I want to go from here to here, I follow the cycle back to this one. So it cannot have cycles. If it had cycles, it would not be the graph consisting of the strongly connected components as a node, because there would be a bigger strongly connected component. That's great. Good observation. Okay. And that's exactly the proof. Good job. If you guys were thinking about that, great work. Okay. So that's the first lemma. Now, we're going to do a couple of definitions. All right. So we're going to say that the finishing time of a strongly connected component is the largest finishing time of any node within that strongly connected component. That kind of makes sense, right? So it's like, when am I done with the entire connected component is whenever I was done with any of the, like the node I was done with last tells me the time I was done with the strongly connected component, okay? The starting time is going to be the smallest starting time of any element in the strongly connected component, okay? So for this strongly connected component, the starting time is 0 and the finish time is 9. Does that make sense intuitively, what we're defining here? And these are just definitions to help us understand why the algorithm works, okay? All right, cool. So what I've done here is now I have created this graph and I have added the starting and finish time for each of the giant nodes, right? Okay. Last time we saw that the finishing times actually allow us to topologically sort vertices. You guys remember that when we learned depth first search? And the whole reason we kept track of the finishing time is so that we could topologically sort it, okay? And topological sort only works on directed acyclic graphs, okay? Because if you have a cycle, then there is no way to sort it where your dependencies are all met, okay? But thankfully, this graph is a directed acyclic graph, right? Which means we can talk about a topological sort for this graph, right? Okay. That topologically sorting this graph also works. If I look at the biggest finish time here, then this is the first thing I need to install that has no other dependencies, right? Because every edge is coming out of it. Does that make sense? So maybe now you're maybe kind of seeing the intuition, or why do we reverse the edges? Okay, so if I'm thinking of this graph, then by the properties of directed acyclic graphs and topological sort, the node with the biggest finish time is going to have no nodes coming in, only nodes going out. Okay. So the main idea is, well, let's reverse the edges. What does that mean? And that means that the strongly connected component, the largest finish time, has no edges going out, right? Because it had no edges going in to begin with. And then I reversed them. So now it has no edges going out, right? So if I run DFS, starting somewhere in this component, it will not have a way to escape. It will discover the entire component, but it will not be able to get out. Does that make sense? Maybe? Any questions? Just kind of trying to explain why the algorithm does what it does, right? So if we start with this strongly connected graph, we can create a topological sorting, right? Using the finish times. If we sort in reverse order of the finish times, that means that this node has no edges coming in. The next node would be this one. And what that means is that the only edges coming in are from nodes that have come before in the topological sorting. So the only edge that's going to come into this node is going to be edges coming out of this node. Okay. And then for this one, it's the last one. The only edges that are going to come in are going to be edges from the nodes that came before. Right. So when we reverse them, what does that mean? That means that if we run our DFS first on this part of the graph, it will complete and find one tree, and it will not be able to escape, right? So that for sure gives us our first strongly connected component, right? Now, if we then run DFS on this part of the graph, what's going to happen? Which nodes am I going to, yeah. Exactly, that's the key. So I will start somewhere in this component. And because they're strongly connected, I will visit all of the nodes here, right? Because there's a way to get to them, right? However, I will never go to this component because every edge for components I have not visited are going to be pointing inwards to me. So I can't get out that way. And I won't go to components before me because I already visited them, right? So I'll check, did I already visit? I did, so I won't go there. So that means that when I run the second DFS, I guess I don't have all the pictures. When I run the second DFS, this is going to be completed. And then when I run the third DFS, the same argument is going to lead to only exploring this strongly connected component. Okay. Now, let's try to make this idea a little bit more formal, I guess. So if you recall, with normal depth first search, we talked about these cases. Remember when we were arguing like why we wanted to topologically sort something? We said, well, there's basically three cases when you're topologically sorting. Either the two nodes you're considering are descendants of each other, right? Or they're not descendants of each other, right? And then we argued by looking at the time, the finish, the start finish time, that no matter what, the finish time of the earlier node was going to be larger than the finish time of the later node, right? So that's what we saw 3-4 days ago. Okay, we're going to say the same thing about a strongly connected component DAG. We'll always have that the finish time will be large if the finish time is larger for this component. Then there's an if graph looks like this. If there's an edge from this component to this component, then the finish time of this component will be larger. Okay. It's actually the exact same proof idea as DFS. We just walk through two cases, right? So now we're talking about the first time we ran DFS. What we're trying to argue is that no matter what, the finish time, if there's an edge in our strongly connected meta graph or bigger graph going from A to B, right? Ignore that there's little nodes inside. If this edge exists, then the finish time of A is going to be bigger than the finish time of B, which means when I run my second DFS, I will start with this component, right? So now this is going like, why do the finishing times of the first DFS help us order which nodes I start with? Okay. There's two cases. We either reached A before B in our first DFS, or we reached B before A in our first DFS. Okay. In the first case, if we reached A before B, then Y, let's say Y is some node, has the largest finish time in B, right? And let's say Z was discovered first in A, right? So we went to A first, then we went to B. Then we reached A first before going to B. That means that we will discover Y via Z, okay? Because Y is a descendant of Z in the DFS force, okay? Then, by the same logic that we used in the depth first search argument, the start time of Z is less than the start time of Y. So Y gets starts and finishes between me starting and finishing, okay? Which basically means that the finish time of B, which is actually equal to the finish time of Y, is less than or equal to the finish time of A, which is what we wanted to show, okay? So this is like a more, like, again, this is just slightly more formal. You don't necessarily need to know this, but if you're trying to prove something, you want to think through every single case. And the thing that you want to take away from this is not, I need to memorize this, okay? It's, I need to be thorough with my thought process, right? I want to be precise. I want to give names to things, and I want to think every single case through, okay? AKA A.finish is bigger than B.finish, which is what we wanted to show. The case 2 is basically the same, is very similar to this one. I'm not going to cover it in too much detail. In either case, the conclusion is that the finish time of A is going to be bigger than the finish time of B, okay? Which is what we wanted to show. So again, the proofs proofs are not like to intimidate you or anything. The proofs are just, if I had to sit down and really think in detail about everything I'm saying, here is the detail of why I think. Okay, so it's a little boring, but it's more about how you think about the problem. Okay, cool. So if there's an edge like this from A to B, then the finish time of A is bigger than the finish time of B, which means in the reversed graph, if there's an edge like this going backwards, then the finish time of A is bigger than the finish time of B, which means that when I start, all the yellow arrows point towards the larger finish times. So again, Jordan, is it Jordan, right? So just like Jordan told us, and like you guys probably noticed from the other graph, what happens is that when we take out this component, we start here because there's no arrows going in or no arrows going out. Then by the time we go to the next component, all the arrows that are going out are going to be going to components we've already processed. So we're not going to escape. And all the other remaining arrows are going to be coming in from components that had a lower finish time, right? And that is why this algorithm works. Okay. All right. Hopefully this is obvious to you. Okay. This should not be obvious. Okay, we spent 2 lectures trying to explain why this algorithm works. So it is not an obvious algorithm. There's a research paper where somebody figured all this stuff out and wrote it out. So hopefully now, after the fact, you guys are like, okay, it makes sense, but you should never say like, this was not easy, this was not obvious, right? Is that clear? So if you're struggling and you're like, I don't understand, that's okay. You should look at the slides again and try to think through every single step of the argument, okay? Because clearly it wasn't obvious since it took me an entire class to just explain it to you, okay? Cool, so to recap, if we run depth first search, it can reveal very useful structures, okay? Last week, we used depth first search to topologically sort directed acyclic graphs, okay? In linear time. Today, we saw that you can also use depth first search to find strongly connected components in linear time. You use it twice, right? You run it once, then you reverse the edges, then you run it again. Okay. This last one here, well, both of these I would say are pretty non-trivial. Okay, this is not something that you should expect to know just by me telling you, here's depth first search, here's a graph, and then you just know how to do this. Okay, but at least you've seen a few. So what we're going to do is these techniques are really useful for other more advanced algorithms. So in the future, when I say the very first thing we're going to do is we're going to topologically sort the graph, you guys will be like, I sort of know how to do that. I just run DFS. We won't go into the details, right? In the future, when I say, oh, we're first going to find all the strongly connected components, you guys are going to say, I sort of know how to do that. I got to run DFS a couple of times, some other details, right? But what you need to know is that it's possible, and it's possible in linear time using depth first search. Cool. All right, so to wrap up today's lecture, we are going to jump into a new topic. I'm going to look at weighted graphs, okay? Directed weighted graphs, and we are going to motivate something called Dijkstra's algorithm for finding the shortest path from any source to all nodes. So let's take a look. So this is a map I found of NCAT. Your maps on the website are very low quality. I could not find a high quality map. So if you guys know somebody that works in the department there, you should hit them up and tell them to put some higher quality maps. All right, please, please. But let's talk about this. Here are a couple of nodes, a couple of locations that I'm going to represent as nodes. I believe I got most of these right. So here's your clock tower. Here's your Aggie Suites down here. Here's us. That's where we are. Okay, that's where we are right now. So you can imagine that you can actually, let's say these are locations that you attend very frequently, right? I don't know if you guys actually go to these very frequently. Did I get one wrong? No? Oh, Eric, I think it's because here's Dudley and here's East Main. So I think this is Eric. Oh, we are. Oh, that means we're here, right? Oh, we're a little off. Oh, that's okay. I'm sorry. I was in my office. Let's say that. Anyway, we're somewhere here. All right. Don't worry about it. So you can imagine each location can be represented by a node. And this is actually, so for my job, when I was working on Google Maps, we basically did this. Okay, where locations are represented by nodes, and we were trying to find the fastest path from one location to another. All right. So this is actually like a very simple example of that. But the only difference between what Google does and what we do in this class is they just have a much bigger graph. So you can imagine trying to connect all of these nodes with edges that maybe represent, you walking from one to the other, or maybe they represent, like, I don't know, maybe from one to the other, you take a bus or something. I don't know, right? They represent the ability to go from one to the other. And at the end of the day, you can actually ignore the entire map. It's just a graph, right? So all the algorithms we've covered so far, you could try to use on this graph. Now, my question to you is, what is given this graph, what is the shortest path from Aggie Village to Aggie Suites? Does anybody live in either of those? Are these like dorm, like freshman dorm place? Yeah, or just undergraduate dorms? Okay, what's the difference? What is Aggie Suites? Is that nicer? Oh, those are dorms. What Aggie Village is? Just different area, something? Okay, I'm gonna go visit all of these, but is there an algorithm? Oh, like Legana lives in suites. All right, so yes, this is great. Good lecture today. How would you figure out the shortest path from Aggie Village to Aggie Suites? Yeah.
Is it first the least number of nodes traveled or distance?
That's a great question. Let's say it's the first one. Do you have an algorithm to figure that out? Do you guys remember an algorithm? We've only covered two basic algorithms, depth first search and breadth first search. Which of those can you use to find the shortest distance based on the number of nodes that you travel? Breadth first search, okay? So you might say, based on what we've learned, hey, let me run BFS on this. I can start it at Aggie Village, right? But then what that tells me is actually the shortest path, according to BFS, is to follow this edge to Aggie Terrace and then follow this edge to Aggie Suites, right? Now, intuitively, you guys, like the real question that I wanted to ask would be, what is the shortest path in time, right? So what's the quickest way to get there? Now, BFS in this example actually gives us obviously the wrong answer. It doesn't make any sense to start here, walk all the way to Aggie Terrace, and then walk all the way to Aggie Suites, okay? So what we need is an idea of trying to add weights to our edges, okay? So what this tells me, you can think of this as maybe the number of minutes it takes me to get from one place to another. So if I go directly from Aggie Village to Aggie Terrace, it's going to take me 25 minutes. I don't know, maybe there's a bus you have to take or something you have to wait. These are just made up numbers that I kind of ballpark estimated. They're probably wrong, but right? So in this case, using the weights, what's the shortest path that I take on this graph? Where do I go? Yeah, Vincent? Clock Tower, and then Health Center, and then Aggie Suites. And how does that take me? 6 minutes, okay? Now, BFS doesn't work with weights, right? But this is so now you guys have been introduced to what we call a weighted graph. So a weighted graph is just a graph where each edge is associated with a weight. Now, here's a quick question. Is this also a weighted graph? What's the weight of each edge? If I wanted to treat this as a weighted graph, could I assign a weight to each edge such that I can call it a weighted graph? Yeah. So that's kind of what we're doing here with the minutes. But I guess the other question I wanted to get at is technically for BFS, you can imagine it's a weighted graph where each edge has weight 1, or where they all have the same weight. It doesn't have to be 1, but they all have the same one, right? So a weighted graph, in addition to the connectivity, we now have a function called W that's going to take in 2 nodes, and it's going to tell us the weight between those nodes. Okay. For now, in this class, and until we come back from spring break, all of our edge weights are going to be non-negatives. Okay. Which kind of makes sense for a lot of useful use cases, right? Like distance is always non-negative. There's no sense of like, if I go from Aggie Suites to like Clock Tower, it's going to take me -3 minutes, right? Okay. Cool. So this is what we call the shortest path problem between U and V in a weighted graph. The cost of a path is going to be the sum of the weights along that path. The shortest path is going to be the one with the minimum cost. Okay. So this path from S to T has cost 25. This path from S to T is shorter. It has cost 5, even though it has more edges, right? So now we're the shortest path problem. This is the definition of the shortest path problem. Okay. The distance between U and V, between any 2 vertices, is the cost of the shortest path between U and V. Okay, so if I say what's the distance from S to T, you will tell me the distance is 5, because the shortest path has cost 5. Okay. For this lecture, all graphs are directed, but to save notation, I'm just going to draw undirected edges, right? All right. So this, like you guys said, is the shortest path from Aggie Village to Aggie Suites. It has cost 6, right? What's the shortest path from the Clock Tower to Aggie Suites? So from here to Aggie Suites, what's the shortest path? It's not a trick question. Anybody can speak up. It's 5, and I go through Health Center and then Aggie Suites, right? So the reason I bring this up is to give you a little bit of intuition, which is more generally a subpath of a shortest path. So subpath is a smaller path that is part of a larger path. It's also a shortest path itself. Okay, say, for example, say this is the shortest path from S to T, right? Let's say, generally speaking, right? You don't have to learn anything, but generally speaking, say that shortest path from S to T. Then this path from S to X must also be the shortest path from S to X. Okay, why? Why are subpaths of shortest paths also shortest paths themselves? Yeah. Yeah. Suppose that there's another path that is actually shorter from S to X, right? Then this path that goes from S to X and then goes from X to T would have been shorter than this path that I said at the beginning was the shortest path from S to T, right? So that's a contradiction, which means a subpath of a shortest path is also a shortest path, okay? All right, going back to the single source shortest path, and you guys saw this actually in the example, right? So you had the shortest path from Aggie Village to Aggie Suites already. The only possible path from Clock Tower, the shortest path from Clock Tower to Aggie Suites must be on that path as well. Okay, if there was another shorter way to get from here to Aggie Suites, then the shortest path from Aggie Village to Aggie Suites would have been go to the Clock Tower and then take that other path, right? Cool. So if I want to know, so this is the single source shortest path problem. And the idea is that I want to know the shortest path from one vertex, so single source, to all other vertices, okay? So here's actually the answer from Aggie Village to all the other vertices we talked about. These are the costs of the shortest paths And these are the paths you take to get there. Okay. So you can double check me on that as the example. This is the answer we want. So what we're trying to figure out is we're trying to figure out an algorithm that, given a single source on a weighted graph, gives us the shortest path from that single starting point to every other node in the graph. That's the goal. Okay. Now, why might this be useful? There's a lot of examples. We're actually at time. So we will pick this back up after spring break, but I do encourage you guys to give it some thought and see if maybe you can come up with an algorithm that solves this problem. All right. And if you can't come up with it, it's called Dijkstra. He came up with it. He was also a researcher, so you can always look it up that way. All right, thanks everybody on Zoom. I will be ending the meeting now, and I will see you guys on Wednesday for your midterm review. Hey, how's it going?